So now how about uniform cost search criteria? So uniform cost search is guided by the path cost rather than the depth of the search, which makes the complexity calculation a little bit is less trivial than the regular BFS. So first of all, is it complete? Yes, it is, assuming that the solution has a finite cost. The problem would be complete. How about the time and space complexity? So for the time complexity for regular BFS, it actually goes level-wise. We have a complexity of the order, remember, of B to the D. B is the branching factor, and D is the depth of the solution, so that will be D. For uniform cost search, we are not going to do exactly a search level-wise this way until we reach level D. However, we're going to do something more that looks more ragged. So we're going to go into this kind of similar thing, but we're going to expand the search until we reach to some level that actually could be estimated as follows. So first of all, let's suppose that we have a cost C star that actually represents the cost of the optimal solution. So it's going to be, instead of D, we are going to use C star. Right? So it will be the depth of the solution. Every action also is bounded by some cost, so which means that we have a cost of at least epsilon that represent a bound on the cost of each action. Afterwards, we're going to be able to calculate the size or the depth of such a solution at with the optimal cost C star. Okay, so the effective depth is roughly, so it's just an estimation, which would be C star divided by epsilon, which means how deep is the cheapest solution, where is it exactly. So C star divided by epsilon will be representing actually the depth of this solution at this level here. So how about the time complexity? So remember, for BFS, we had the time complexity of which is a big O of B to the D, where B is the branching factor and D is the depth of the solution. So typically we have the search space, it's a search tree, and we have the solution at assignable level D. And the breadth first search, again, will do a level-wise search until it actually reach the level D where the solution is. Uniform cost search will not really do it in such a level-wise. It's going to be a little bit kind of drag because it's going to look it. It's going to still do some kind of, but it's going to be until it reaches the level of the solution D. Actually, here, how can we define D? D is not really defined as a specific level because we are going to move to the search space based on different costs. So we're going to estimate it. And the way to estimate it is, first of all, let's suppose that C star is actually the cost of the optimal solution. So the optimal solution would really have some, let's say, number of kilometers. We suppose also that the action cost, each action cost is bounded. So we have every action would cost at least epsilon. Yeah, given C star and epsilon, we could estimate the effective depth, which is roughly C star divided by epsilon. We need actually to, here the idea is to be able to estimate, instead of D, we're going to have C star divided by epsilon, which is an estimation of the depth of the solution based on our search based on the costs. Okay, so in this case, instead of big O of B to the D, we're going to have a cost of, in this case, of B to the C star divided by epsilon. So this will be, this is just based on what we estimated as the depth of the solution given this strategy. Similarly, we also estimate the space complexity using this estimation of the depth of the search. So for space complexity in the regular BFS, we had also B to the D. The D now is also replaced by C star divided by epsilon, which represent our estimation of the depth. Is the solution optimal? Yes, it is. It's going to really search for all the costs until it finds the least cost path if there is a solution. Okay, so implementation, as we said, it's also a queue, just like BFS, but it's, in this case, what we call a priority queue that is ordered by the path cost based on the cost function g of n, which is the lowest first, which is actually implemented as a heap. Okay, so that was for the complexity. So uniform cross search has great features that it is complete and optimal. However, it also explores the space in every direction because no information about the goal is provided. So we are prioritizing this in this case not by depth but by cost, which means that suppose we have a start state here and the goal is here. What will happen is that the search will go around the start by, let's say for the map, increasing the length of the radius. So we're going to look around and around. So the search will be really exploring the area and going bigger and bigger in terms of the search until we hit the goal G. So you could see that that's really a waste of resources, a waste of time in searching around the start space. And we would love to really use some information about the goal in order to go really straighter to this goal rather than exploring and wasting time looking around based on the cost.